Okay, folks, can you hear me? Hello, can you? Yes, okay, good. All right, we have a minute before we begin. So do we have any questions from the last class? Any questions? Any questions about the logistics? None? Okay. So today, while I lecture, I'm going to pause at various points and ask you if you have understood what has been presented so far. And when I do that, this Zoom actually gives you the ability to show a thumbs up. You don't have to show me a thumbs. You can just mark a thumbs up and I can count the number of thumbs ups or count the number of hands shown on Zoom. And so I will actually check that to make sure that a majority of you have understood whatever it is I'm trying to convey before I continue. So please, anytime I ask you to give me a show of hands to confirm that you have understood what has been presented, please do so, right? Rutvik, there will be project presentations for 11785. It's all on the course page, right? So, and check lecture 0. All right, let's begin, right? Uh, the so Jack, you will have to watch the video on MediaTek. We give you some amount of leeway until the course ad deadline because people join late. But if you don't watch the lecture, you're not going to be able to answer the quiz. And so please watch the lecture for your own sake anyways, right? All right, let me begin. Here are the topics for the day. We've introduced neural networks in the previous class. Today, we're going to go a little deeper into what neural networks can represent and what the restrictions are for these representations. And when I'm speaking of restrictions, I speak of restrictions in terms of depth and width of the network and the activations that we use in the network. So here's what we saw in the last class. Neural networks have taken over AI starting about 2016, and tasks that were once assumed to be purely in the human domain of intelligent expertise are no longer have actually been made possible by neural networks. And in fact, in many of them, they outperform human beings by a large margin. So what exactly are these neural networks which do all this magic? They are these boxes which take in some input and produce an output. Like a neural network that does voice recognition takes in a voice signal and produces a transcription. Or if it were performing image captioning, it would take in an image and generate a caption. Now, things that take in an input and produce an output are functions. And so these neural networks are functions. But what are these functions? Now, in a human being, those functions are computed by the human brain. And so, in their basic form, as we saw in the last class, neural networks mimic the networked structure in the human brain. And we also saw that the brain is composed of a network of these basic elements called neurons. And so, artificial neural networks, too, are composed of networks of simple computational elements, where these elements are computational models of the neurons. These are our perceptrons. And the perceptron, we saw in the last class, mimics the human neuron, roughly speaking. It's a threshold unit in its most basic form. The perceptron obtains a number of inputs. Corresponding to each input is a weight. If the weighted sum of inputs exceeds a threshold, the perceptron fires, otherwise it does not. So here is the mathematical representation of how the perceptron operates. It computes a weighted sum of the inputs. If that exceeds a threshold, it fires, that is, it outputs a 1, otherwise it outputs a 0. Now, this unit is what electrical engineers will call a threshold gate. It's a basic unit of Boolean circuits. Now, here's a slightly modified and possibly better figure for it. Instead of computing a weighted sum of the inputs and comparing it to a threshold, I can redraw it in this manner, where you're computing a weighted sum of the inputs plus a bias. And so what we are computing is an affine function of the inputs. Again, does anybody remember the difference between what is an affine function and what is a linear combination? Anyone? The bias, right? So if I say summation wi xi, this is a linear combination. But if I say summation, and so when I equate this to 0, this is going to give me the equation of a hyperplane that goes through origin. On the other hand, if I say summation wi xi plus b, this is an affine combination. If I equate this to 0, then this is also going to be the equation for a hyperplane, but that equation, that hyperplane will not go through origin. And so what we do here is first to compute an affine combination, an affine function of the inputs. And this affine function is put through a threshold activation. So this is perceptron here is exactly the same as the perceptron here. We're just stating it differently. Within the perceptron, we first compute an affine function of the inputs to get an affine value z. This affine value is put through an activation function, a threshold activation, which outputs an 1 if its input is positive and 0 otherwise. And so this is our perceptron. Now, once we separate things out in this manner, we can replace this activation with other functions. So for example, instead of having a threshold over here, I can have something that's looks like a threshold, but it's smoother. This is the sigmoid activation. And so in this version of the perceptron, the affine value computed from the input is processed by the sigmoid activation. You can also have other activations like the tan-H activation, which looks like the sigmoid, but it goes from -1 to 1 instead of going from 0 to 1. Or these activations over here, this is the rectification function, also called the rectified linear unit, the red line. For positive inputs, the output is the same as the input. For negative inputs, the output is 0. Or this blue line, this blue curve, which is called the soft plus, is a smooth version of the rectification function. All of these are different activation functions that we can use on the affine term that you compute from the inputs. For the purpose of this lecture, however, we're going to continue to assume a threshold activation that operates on this affine function of inputs. So the perceptron that we will be working with is the original basic perceptron. And so here is our first poll. Let me release it. This is, can you see the poll? Vihan, there's no attendance poll because I'm going to get the attendance off Zoom. Okay. 5 seconds, guys. All right. Let me stop this. Okay. Here's what your results were. If you can see it. Stop sharing. Does anybody want to answer me? Is this first statement true? 3x plus 7y is a linear combination. Is the second statement true? False, right? The third statement, is this true? This is true, right? And the fourth statement is also true. And so it turns out that this is a linear combination, but linear combinations are a subset of affine combinations where the bias is 0. So the first, third, and fourth statements are true, right? And so let's move on. So we've defined our perceptron, but then we found that we really want to work with networks of perceptrons, multi-layer perceptrons, where you have many such perceptrons which are connected to each other in layers. What is a layer? We'll get to that shortly. And so we have a layered network of perceptrons. This is a multi-layer perceptron. And now the kind of networks we are speaking of are deep networks. So what is a deep network? Now, in order to define a deep network, first we have to define depth. So what is depth? Depth is defined in terms of graphs. Now, how many of you know what I mean by a directed acyclic graph? Does anybody know what a directed acyclic graph is? So what is it? It's a directed graph, which means that we all know what a graph is. Graphs have nodes and edges between the nodes. And a directed graph is one in which the edges have directions, as shown by the arrowhead. It's acyclic if there are no loops. Now, anytime you have a directed acyclic graph of this kind, you're going to have nodes which are sources. These are nodes from which all the edges go out. And you have nodes which are sinks, nodes where all the edges come in. And when you have a directed acyclic graph of this kind, the depth of the graph is defined as the longest path from a source to a sink. So in this graph, I have a path of length 1. This is the source, this is the sink. I have a path of length 1. But I also have a path of length 2. So although there's a path of length 1, the longest path is length 2. So the depth of this graph is 2. Here's another graph. This graph also has a source and a sink. There's a path of length 1 between the source and the sink. There's also a path of length 2 and a path of length 3. What's the depth of this graph? Anyone? What is the depth of this graph? 3, because the longest path is 3, right? And so when we define neural networks, you can perceptrons feed perceptrons. So there are outgoing edges, all the connections are directed, and you have paths going from the source, which is the input, to the sink, which is the output. And the depth of the network is the length of the longest path from any input to any output. So in this network, for example, you have neurons essentially arranged in layers. Again, we'll get to layers in a bit. And so if you take any path from a source to a sink, it has to go through 1, 2, and 3 neurons. So the depth of this network is 3. And if the depth of the network is greater than 2, then we call it a deep network. So here again, these are the output neurons. These are hidden neurons because we are not really interested in their precise outputs. We are only interested in what's coming out here. And so we have 2 hidden layers and 1 output layer. But we have the length of any path is 3. So this is a deep network. What is the depth of this network? Anybody? What's the depth of this network here? 2. This one here on top is, okay, is it a deep network? This one, is this a deep network? No, right? 1, 2. So the depth of this network is 2. What's the depth of this network at the bottom right? Anybody? 4. 1, 2, 3, 4. Is it deep? Yes, right? So beautiful. We get it. Now I'm speaking of layers, but what is a layer in this case? Visually, it's very apparent what a layer is. But then if I draw a network like this, you might be fooled into thinking this is a layer. But no, there is a formal definition for a layer. A layer is the set of neurons that are all at the same depth with respect to the input, which is the source. And so the depth, and the depth of the layer is the depth of the neurons in the layer with respect to the input. So here, for example, can you tell me which are the neurons which form the first layer? Layer 1. Anyone? Which neurons would form the first layer? The left, no, this is the input. This is the source, right? So this is not the first layer. And so what would be are these the first layer? These guys, these 4 red neurons are all at depth 1 with respect to the input, right? So these are all at depth 1. The longest path from the input to these neurons is length 1. So these form the first layer. The second layer. Now look at these green neurons. These green neurons also have a direct path from the input. But if you consider the longest path from the input to these green neurons, it's 2. It's 2 for this guy, it's 2 for this guy, and it's 2 for this guy, right? So the green neurons form the second layer. The yellow neurons, they do have paths which are only length 2, but the longest path is length 3. So the 2 yellow neurons are the only neurons which have a path of length 3. So the 2 yellow neurons form layer 3. And the 2 blue neurons form layer 4. Is this making sense? Just confirm, right? So although visually, what you might think of as layers would be very different, if you go by the formal definition, this is how the layers are arranged. And so we have the blue neurons. In this case, the blue neurons are the output layer, okay? And so we have a multi-layer perceptron, which are networks of neurons connected in layers, and they're directed generally. And the neurons themselves are the basic perceptron. Now, we saw from the last class that in this kind of a network, inputs could be boolean or real. Outputs could be real or boolean. And although in this figure, I have just drawn a single output, you can have multiple outputs in the network. And so now the question is, what kind of relationships can this network compute? What kind of input-output relationships can it model? So for this, let's go back to the last class. We know already that MLPs can compose Boolean functions. We saw that they can compose any Boolean function. We also saw that MLPs, this S should be a P, can compose classification boundaries. So these are category functions where you say within this region, I'm going to output a 1. Within this region, I'm going to output a 2, and so on. So MLPs can be arbitrary classifiers. We also saw they can compose real valued functions. But are there any limitations to this? That's what we're going to explore. And so today, we're going to look at multi-layer perceptrons as universal Boolean functions and the need for depth. We'll look at them as universal classifiers and the need for depth, and as universal approximators. And we will discuss optimal depth and width. So let's look at the first issue. MLPs as universal Boolean functions. Now, what do I mean by saying that an MLP is a universal Boolean function? For that, we start off with how well do MLPs model Boolean functions? Now, we already know that an individual perceptron can model any Boolean gate, right? What was this gate over here? Anyone remember? What was this gate? This was the AND, right? And this guy here, this guy was an OR, and this was a NOT, right? So we saw that a perceptron can model any simple binary Boolean gate. But in fact, a perceptron is much, much, much more powerful than a Boolean gate. A single perceptron can perform computations that would require an exponential number of Boolean gates to perform. So here are some examples. Look at this network, right? Look at this perceptron. It has n inputs. The weights corresponding to the first L inputs are all 1. The weights corresponding to the rest of the inputs are -1. The threshold is L. What kind of output does this produce? Can anybody guess? What will this produce? Anyone? Does anybody want to take a guess? Okay. This one, this is going to produce an output of 1 if and only if these guys are all 1 and these guys are all 0. Under this condition, the total input that comes in over here is going to be L. If I flip any one of these guys, this is going to become L minus 1 and it will not fire. So also if I flip any one of these guys, this is going to contribute a minus 1 to the sum. And once again, the sum will decrease and this will not fire. So this will only fire if these guys are all 1 and these guys are all 0. This making sense to all of you guys? So, and there was one person who asked why. Hannah. So, Hannah, what was your doubt here? So, Hannah Kasim, yeah, you were not sure. I don't understand why this has to be 1. Okay, consider this. These are the weights, right? If all of these guys are 1 and all of these guys are 0, what is the total that comes in here? What is the total that comes in here? L. If I flip one of these, what is the total? If I flip one of these, what is the total, Hannah? L minus 1, right? Okay, let's say I keep this guy, but I flip one of these. What is the total? If I make this a 1, because the corresponding weight is minus 1, then 2, it becomes L minus 1, right? So literally the only condition under which the total here is going to be L is if all of these guys are 1 and all of these guys are 0, right? And so this single perceptron models this very complicated Boolean function, which says all of these must be 1 and all of these must be 0. And then and only then is it going to fire. Make sense? Right? And so here's another one, right? This guy is going to fire if any of these first L is a 1 or if any of these guys is a 0. Can you figure out why? Anybody? Why would this work that way? Anyone? Why would this work this way? So let's see the condition under which it doesn't fire, right? It doesn't fire if only condition under which it doesn't fire is if all of these are 0 and all of these are 1, right? So because under this condition, the total sum that comes in is L minus N. Because these have a weight of minus 1 and these have a weight of 1. And so these are all contributing 0. You have N minus L of these guys. They all have weight minus 1. So the total that comes in is L minus N, right? If I flip any one of these, this is going to become L minus 1 plus N plus 1, which means that if any of these is flipped, it's going to fire, which means that this will fire if any one of these guys is a 1 or if any one of these guys is a 0. So this is what I will call a universal AND gate. The previous one, I can create a single perceptron for any kind of ANDing. Here's a universal OR gate. But then, is this making sense? Yes, no. Right. Okay, and here's something even more interesting. This is a majority gate. This will fire if and only if, so which one, this last one? So here we'll run out of time, right? But post it on Piazza and I can explain, right? Now consider this one here. So this will fire if any set of k inputs or more, k or more inputs is 1. Does this make sense for this one? Right? The threshold is k. So if at least k of the inputs are 1, it's going to fire. if you want to build a Boolean circuit for this kind of operation, you have to consider every combination of k inputs for a single perceptron. So that's going to be exponentially sized. And that exponentially sized circuit is replaced by a single perceptron. So perceptrons are very, very powerful, right? Yet, we know that in spite of all their power, which is why for a very long time people thought that perceptrons were universal Boolean machines, but they're not. We know this because we know they cannot compute an XOR from the last class. We saw that for an XOR, we need a multi-layer perceptron. You have this hidden layer. The first one computes XOR Y, the second computes not XOR not Y. The output perceptron ends the two. And now you have an XOR, right? Everybody remember this? Yeah, they're the same thing. So, in fact, it turns out you don't even need 3 perceptrons. You only need 2 perceptrons. This picture was, I got this circuit from my friend Gerald Friedland in Berkeley. Here's a multi-layer perceptron with only 2 neurons and 5 weights and 2 thresholds, and it too computes the XOR. But you need at least 2 perceptrons. But once you realize that I can compose Boolean gates with perceptrons. So I can compose any Boolean circuit, which means that if you give me a Boolean function, I can compose a multi-layer perceptron for it. In other words, multi-layer perceptrons are universal Boolean functions. For any arbitrary Boolean function, there is an MLP that can compute it. That makes sense? That MLPs are Boolean functions. So, okay. Give me thumbs ups, guys. I can count the number of thumbs up here, okay? And the next time I ask, I'll wait for 100 thumbs ups. And so MLPs are universal Boolean functions. Any function over any number of inputs and any number of outputs, I can compose an MLP for it. But then, how many layers will this MLP need? Now, in this example, I have 3 layers. I can have other circuits with 4 layers, right? And so one might assume that the number of layers required for the MLP is going to be dependent on the complexity of the Boolean function itself. So before I go down that line, I'm going to ask you guys a question. What is the smallest number of layers that an MLP will need to model any Boolean function in the worst case? So Preet, you say 2. Why would it be 2? Can anybody tell me? Why is it 2? Anyone? XOR requires 2. XOR is just 2, but of standard Boolean, any complicated Boolean function, why would it be 2? So here's why, right? Any Boolean function can be written as a truth table. These are all the input variables. This is the output. And this is the combination of input values for which the output is 1. So the first row of the table is written as the output is a 1 when x1 is a 0, x2 is a 0, x3 is 1, x4 is 1, x5 is 0. And so I can list out every combination of inputs for which the output is a 1. I only need to list out these combinations. For all other combinations, the output is implicitly 0. Once I write it like this, I can write this Boolean function. So this is any Boolean function. It can be written as a truth table. And then the Boolean function can be written as a disjunctive normal form, where it is an additions of multiplications. Addition represents OR, multiplication represents AND. So I can say this first row says the output is 1 if I have not x1, meaning x1 is 0, and not x2, and x3, and x4, and not x5. So that's this first clause over here, right? Or the output is 1 if I have not x1, x2, not x3, x4, and x5. That's the second clause. Or if I have not x1, x2, x3, not x4, not x5, right? And what is this clause? Anyone? What would this clause be? Over here, the fourth one. Someone want to hazard this? I'm sure you guys know. It's going to be x1, not x2, not x3, not x4, x5, and so on, right? And so for each of these 6 rows, I have 6 clauses. And they're all odd. But once I write it this way, I can build an MLP very trivially. One perceptron for the first clause, one for the second, one for the third, one for the fourth, one for the fifth, one for the sixth, I odd them all. And so once I express my truth table in disjunctive normal form, I can build the MLP with just one hidden layer to represent the Boolean function, regardless of how complex this Boolean function is. So any truth table can be expressed in this manner, which means a one hidden layer MLP is a universal Boolean function. MLPs with just one hidden layer can express any Boolean function at all. These are universal Boolean functions. But then, if I want to express this with just one hidden layer, what is the largest number of perceptrons I'm going to require in this hidden layer if I have n inputs? Anybody want to guess? If I want to take any odd Boolean function and build it with just one hidden layer. So Daniel Ragazzo, why do you think it's 2 raised to n? Or anybody who says 2 raised to n, why is it 2 raised to n? Anybody, do you want to tell me? All the combinations, right? So to explain here, so look at this. How many of you are familiar with Karnaugh maps? Anybody familiar with Karnaugh maps? So a Karnaugh map is basically a truth table. It's just a topologically arranged truth table, right? Here's a Karnaugh map of 4 variables, wx and yz. The 4 rows represent all combinations of wx. The 4 columns represent all columns of yz. Adjacent rows differ by only 1 bit. So every cell over here represents a combination of 4 bits. This cell is wx is 0, 1, yz is 1, 1. And here I can just, so observe that every cell, every row differs by the next row by just 1 bit. Every column differs from the next column by just 1 bit. And the leftmost column is connected to the right column, rightmost. They differ by only 1 bit. The topmost row is connected to the bottommost row. They differ by only 1 bit. So this is actually a toroid. And now I can just color up the cells for which the output is 1. And so in this function of 4 variables, I have 7 combinations where the output is 1. So if I were to write a simple DNF formula, the basic DNF formula would require 7 terms in the clauses. And so a one hidden layer network is going to need 8 neurons, the 7 clauses and the final OR, right? So Delphine, the DNF formula is this guy here, okay? But then we can begin grouping things. The nice thing about arranging things in a Karnaugh map is that adjacent cells differ by only 1 bit. So now I can group up this entire column. When I group up this entire column, it tells me that it doesn't matter what W and X are. So long as Y and Z are 0, 0, the output is 1. So now I can have a single clause for this group which says not Y, not Z. Similarly, I can group these two guys. And what these two guys tell me is that it doesn't matter what Z is, so long as Y is 0 and WX are 0, 1, the output is 1. And so I get a clause, not WX, not Y. Similarly, here I've grouped these two. In fact, you can group the 4 corners. And so that group is going to give me not X, Y, not Z. So although there are 7 terms in my Karnaugh map, 7 cells, the DNF formula can be reduced to having only 3 clauses. And so the one hidden layer MLP will have just 3 neurons in its hidden layer, although there are 4 inputs. It's small. So Lingyun, here, look at this. You look at this vertical group. What is it telling us? That it doesn't matter WX, what W and X are. So long as YZ is 0, 0, the output is 1, correct? So Lingyun, you see that? Yeah. So which means that anytime you have adjacent cells, which are colored, you can group them up because they differ by only 1 bit, and that bit is basically irrelevant, right? And so you can reduce these clauses. But then, what arrangement of ones and zeros simply cannot be reduced further? Anyone? Which arrangement cannot be reduced? A checkerboard, right? This is simply not going to be reducible. So in this case, if I want to have a DNF formula, how many neurons will I have in the one hidden layer? How many clauses will it have over here? Anybody? How many clauses will it have? It's going to have 8 in the hidden layer plus the one output, right? So, and similarly, here I've drawn a three-dimensional Karnaugh map in 6 variables. And of these 3 dimensions, again, it's a 3-dimensional checkerboard. There are 64 cells in all. How many of them, but how many clauses would I have in my DNF formula? Irreducible DNF formula. I'm going to have 32 clauses and the output, right? So in general, if I have n inputs, I'm going to need 2 raised to n minus 1 perceptrons in the hidden layer for this worst case. It's exponential. The size of the hidden layer is exponential in the number of inputs. That making sense? Over here? Yes, no? Okay. Okay. Just give me thumbs up, guys. So here is my second poll. And let me release poll 2. Okay, 15 seconds, guys. Okay, let me stop this. And this is what you came back with. Let me stop sharing this. And what is the answer? Anybody? 512, because you have 10 inputs. So 2 raised to 10 combinations. Every alternate combination is in the clause. So 2 raised to 10 divided by 2, that's 2 raised to 9. That's 512, right? That's the correct answer. So this can be generalized. This is going to require 2 raised to n minus 1 perceptrons in the hidden layer. But if I use more than one hidden layer, how many perceptrons will I need? For this, let's go and look at the formula again. This guy, this is just an XOR. Anytime you flip one bit, the output changes. That's an XOR, right? So this is W XOR X XOR Y XOR Z. This is an XOR, U XOR V XOR W XOR X XOR Y XOR Z. An XOR function is one where the output flips anytime you flip a single bit, right? So anytime you slide by one cell, the output is flipped. And we know that an XOR can be built using only 3 perceptrons. In fact, I can build it using 2 perceptrons, right? And so this guy over here, I can just have a W XOR X, XOR that output with Y, XOR the output, that output with Z, right? And so this whole thing is going to need one set of 3 perceptrons for each XOR. And you just have about as many XORs as the number of inputs, minus 1. So this one required only 9 perceptrons. In this case, it's an XOR of 6 variables. So there are 5 XORs over here. I can build a circuit over here. U XOR V is 3 perceptrons. XOR the output with W, 3 perceptrons. I'm going to need only 15 perceptrons. And so, more generally, once I begin to go deep, the XOR of n variables is going to require 3 times n minus 1 or even 2 times n minus 1 perceptrons. So here's the lesson, right? If I use a single hidden layer, this is going to require 2 raised to n minus 1 plus 1 for the output unit, perceptrons. So with a single hidden unit, the number of perceptrons required is exponential in the input. If I let the network go deep, like here, where I have many hidden layers, I can get away with just 3 times n minus 1 or even 2 times n minus 1 perceptrons, which is linear in the number of inputs. And so depth allows the size of the network to go from being exponential in the inputs to linear in the inputs. Now, how many layers do you need for this to work? You need, 2 log 2 of n layers. You can't go below that, but the smallest number of layers you can get away with is 2 log 2 of n. Why so? Because the XOR is associative. So if I have x1, XOR x2, XOR xn, and so on, I can rewrite it this way. I can XOR x1 and x2, x3 and x4, x5 and x6. I can XOR all of the inputs in pairs. So these are the XORs of the inputs, pairs of inputs. I can XOR their outputs, as you can see in this rewritten formula over here. And so I can pair those up and XOR them. Then I can pair those outputs up and XOR them. So when I do this, I'm going to have one block. I can have several blocks. Within each block, the number of outputs is reduced in half because I've taken pairs of inputs and produced a single output. And so how many such blocks will I need to go down to to one output? If the number of variables is reduced in half in each layer, how many blocks will I need? Anybody? Log n, right? It's going to be log 2 of n. Does everybody agree? Yes or no? And so you're going to see that, and within each block, you need 2 layers. And so you need only 2 times log 2 of n layers. And so 2 log 2 n layers is going to give you the minimum depth required for you to be able to construct the network with a linear number of neurons. What would happen if I go below these number of layers? So Aditya, it's log 2 because I'm pairing things, right? What would happen if I go below these number of layers? So exponential. Aditya, look, at each point, the number of terms is being reduced by a factor of 2, correct? So at each point, if I start off with n variables here, I'm going to have n minus 2 here, n over 2 over here. I'm going to have n over 4 over here. I'm going to have n over 8 over here. So that's log base 2. So here is what will happen. If I decide that I'm not going to use log 2 n layers, that I'm only going to use 4 layers, then the best thing you can do is you can keep reducing the number of variables by half. And then at some point, you're going to get some number of variables which must eventually still be XORed. And you will have only one more hidden layer. And that one hidden layer is now going to be exponential in size. And so anytime you have a fixed depth to the network, then at least one of the hidden layers is going to have to be exponentially large. So long as this is satisfied, you can get away with a linear number of neurons. That makes sense? Yes or no? Right? And so what happens if I don't have these many neurons? If I get rid of just one neuron, what will happen? Anybody want to guess? I say I'm not going to have these many, I'll just kill this one neuron. What will happen? Anyone? Loss? Here's a magic about the XOR function. If you miss one bit, the XOR's error rate becomes 50%. Basically, it becomes random. If you just miss one bit, it's going to become a random function. And so just losing one neuron in this collection is enough to make your entire circuit completely useless. And so here's where we are. Deep Boolean MLPs that scale linearly with the number of inputs can become exponentially large if recast using only one hidden layer. So in summary, an MLP is a universal Boolean function, but can represent a given function only if it's sufficiently wide, it's sufficiently deep, and depth can be traded off or sometimes exponential growth of the width of the network. And optimal width and depth depend on the number of variables and the complexity of the Boolean function, where complexity and quantifying in terms of the minimal number of terms and the DNF formula for the function. So here's the story so far. MLPs are universal Boolean functions. Even a network with a single hidden layer is a universal Boolean machine, but a single layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons than shallower networks to express the same function. They could be exponentially smaller, right? So we've seen Boolean functions, but let's look at classifiers. We saw how MLPs operate over real inputs. An MLP can find a complex decision boundary over a space of reals. We saw this in the last class. The way we do it, a single perceptron models a Heaviside function, a step function. It outputs a 1 whenever the weighted sum of inputs matches a threshold, so is greater than a threshold. So the boundary between where the output is 1 and where the output is 0 is where the weighted sum is exactly equal to the threshold. That's the equation for a hyperplane. So there is a hyperplane in the space where on one side the output is 1 and on the other side the output is 0. And so a single perceptron looks like this. The output is 0 on one side of the hyperplane, 1 on the other side. If I use 0 and 1 as class labels, it's a linear classifier. It's separating the classes with a single hyperplane. But then once you see that, we also see how we can compose Boolean functions with it, right? So if I draw my boundary over here for Boolean inputs, what was this Boolean function? Anybody? You remember? What was this? It was an OR, right? This was a NOT. And now you can see why a single perceptron cannot model an XOR. An XOR has two boundaries. A single perceptron can only capture one boundary. For an XOR, the output is 1 between these two boundaries and 0 outside, which is why a single perceptron cannot model an XOR. And so here is our third poll. Let me release it. Wait, why am I unable to release the poll? Has somebody released the poll already? Okay. Can you see the poll? Fifteen seconds, guys. Okay. Let me end this here. So here's how you answered. And what's the answer? True, right? An XOR network needs two hidden neurons and an output neuron because we want one for one boundary and the other for the other boundary, and then you're ANDing them, right? For the two neuron perceptron, you actually end up with one perceptron capturing the other boundary, and the second is working on the output of the first perceptron. So you still end up getting the same kind of boundary structure. But then we saw how we act. Once we do that, we can compose more complex decision boundaries like this one. For this pentagon, I'd had one perceptron here, one here, one here, one here, and one here, or their outputs, and their outputs. And now voila, I have an output, which is a 1 inside the pentagon and 0 outside. And then once I can build a pentagon, I can build things like double pentagons we saw yesterday out in the last class. One subnet for the first pentagon, another for the second. Then I OR the lot. I can have more complex decision boundaries like this one here, where all I need to do is to partition the decision boundary into little polytopes, have one perceptron for each polytope, one subnet for each polytope, and OR the lot. So we can compose all kinds of decision boundaries. But then, arbitrarily complex decision boundaries. But can I do it using just one hidden layer? So let me ask you this. Can you think of how I could build a one hidden layer NLP for this decision boundary? Anybody? Any ideas? How could you do this? I'll give you 15 seconds, then I will answer you. Nobody at all? No one wants to hazard a guess? One neuron. Here's what. You can't just say, I'm going to have one neuron for these guys and one neuron for all of these guys and them, because if you do so, then what will happen is, look at this. For a single uh, pentagon, you had this region where the sum was 4. If you have another set of neurons for the other pentagon, they too will have a sum of 4 over here. The total is going to become 8. So oddly enough, you will have a higher sum outside the region than inside. So you can't just compose things up so trivially, right? It's not going to be possible. So here's what we're going to do, right? Let's go back and look at our problem polygons again. First, consider this polygon net. Here, I've built a network to output a 1 inside a diamond and 0 outside. So I would have one perceptron for each of these 4 boundaries, and their outputs are summed, right? But then if you look at the output value over here, the output value, which is the sum of these 4 outputs, is 4 inside the diamond. It's going to be 3 in these yellow regions, which go all the way to infinity, and it's going to be 2 in these white regions. This making sense? Over here, this figure. And so if I draw the sum, not the thresholded value, but the sum, this is what the sum is going to look like. 4 over here, 3 in these regions, 2 elsewhere, right? Which is why if I use a threshold of 4, I'm going to get a perfect diamond decision boundary. But observe that the area of the regions where the sum is 3 is infinite, right? Now, let me go up to a pentagon. If I go up to a pentagon, I'm going to have one boundary, one perceptron for each of these boundaries. But when I sum their outputs up, the sum is going to be 5 inside the pentagon. It's going to be 4 inside these little triangular regions. It's going to be 3 here and 2 in these corners, right? Which is why if I apply a threshold of 5, I get a pentagon decision boundary. But here's the sum. The sum to which I would apply the threshold, this is what it looks like, okay? If I go up to a hexagon, here's what the sum looks like. It's 6 over here. The regions where the sum is just below 6, 5 is smaller, and so on. Now, the key to all of this is these regions where the sum is not 6, but close to 6. Because if I have multiple polytopes, and each of them produces a sum that's close to the peak, but not equal to the peak, if I attach them up, their sum is going to be the 5 from the first polygon and the 5 from the second polygon will sum up to 10 over here. If I just begin patching these together, I cannot. So just keep observing this 5. This n minus 1 region, it became smaller. So here I have this with heptagon, where I have a polytope with 7 boundaries. Here's where the sum is 7. This is where it's 6. This is where it's 5. This is where it's 4. This is with 16 sides. This is with 64 sides. Where do you think we're headed? What will happen in the limit? Anybody? Does anybody want to guess? If I keep going down, right, eventually, as I keep increasing the number of sides, this is what you're going to get. That with infinite neurons over here, infinite sides, that function or approaching infinite, it's going to become something like this. It's a circle, it's a flat circle on top. And from there, it falls off exponentially. So if you have n neurons, the sum is going to be n over here and n over 2 everywhere. And so you can approximately model this as something like this. It's a perfect cylinder where the sum inside the cylinder is n and outside the cylinder is n over 2. And so my network over here, if you look at the sum over here, that sum looks like this figure, right? It never goes over n over 2 because at any point, as you go around, at least half of them will be on the one side. You can check this out, right? Plus or minus 1. So in the limit, it's going to be n over 2. And so here's something, if I can just add an extra bias and subtract out the n over 2. And now inside the cylinder, it will be n over 2, and outside it's going to be 0, right? And so now here's what, suppose I want to have a decision boundary that's two disconnected circles. Here's what I can do. I can have one subnet where the sum of all of these neurons composes this first cylinder. Another subnet where the sum composes the second cylinder. If I sum the outputs of these two subnets, because these two cylinders are not intersecting, the overall network is going to produce this output just before the threshold, where the sum of the outputs of all of these perceptrons is two cylinders. This making sense? Over here? Yes or no? Right. Can I get a few more thumbs ups? Like I have 3 out of 300 people telling me yes. Maybe 25 would be nice. Okay. All right. So, and now if I use a threshold of n over 2, I'm going to get a perfect double circle decision boundary. And so now I know how to compose this guy, right? I'm going to fill it up with circles. I can make the circles arbitrarily thin and compact them arbitrarily tightly. And so eventually I will be able to approximate this double pentagon to arbitrary error. You give me an error bound. You say, I want at least 99.99999% of the double pentagon to be exactly filled. I can build you a network for it. Regardless of what error you specify, I can build a network that gives you an error lower than that. So I can achieve arbitrary precision. And so, yeah, MLPs, that's right, 100, are universal classifiers. They can capture any classification boundary, but even a one hidden layer MLP can model any classification boundary, which means MLPs are universal classifiers. One hidden layer MLPs are universal classifiers, but you know what? This is where depth comes in. If I allowed myself two hidden layers instead of just one, with one hidden layer, I needed infinite neurons in that hidden layer. The moment I allowed myself two hidden layers, I got away with just 12 hidden neurons. So deeper networks are going to require far, far fewer neurons than shallower networks to model the same function. This making sense? Yeah? Give me a thumbs up if it does, right? Okay. So we saw this very simple double pentagon, but let's look at a different pattern, worst case decision boundaries for threshold activation networks. It generalizes to other nets. A naive one hidden layer neural network, if I want this decision boundary, where I want ones inside the yellow regions and 0 in the gray regions, if I try to build this using a naive one hidden layer network, we just saw you need infinite hidden neurons. But then with two layers, I just need 56. Why? 56 hidden neurons. Why? This hash is composed of only 16 lines. So in the first layer, I need 16 neurons, each one of which captures one of these boundaries. The next layer is going to have one neuron for each of these bright cells, which says that, this one might say, for example, I want to be on the right of this, above this, and to the left of this, and so on. And so I'd need one neuron for each of these bright cells. There are 40 of these yellow regions, so I'd need 40 neurons over here. 40 plus 16, 56, plus this one. So with two hidden layers, I can get away with 57 neurons. But then, this is a hash cross hash. It's just an XOR. If the first layer neurons output the variables y1 through y16, This guy is just an XOR of y1 through y16. And so if I let myself go deep, there are 16 variables, 15 XORs. An XOR needs 3 neurons. So, the 16 neurons for the first layer plus 3, there are 15 XORs, 3 times 15 neurons. So I could get away with 16 neurons. If I use the 2-neuron XOR model from Friedland, in fact, I could do this with just 46 neurons as opposed to 57 neurons. Now, that doesn't seem like a big win. If I go to a more complex, slightly more complex function like this one, which is a grid formed of 64 lines, where the network must output 1 in the yellow regions, then I need 64 neurons in the first hidden layer, to capture these 64 boundaries. And then there are 544 of these yellow cells. So I'm going to need 544 neurons over here. So there are a total of 544 plus 64, 608 hidden neurons, 609 total neurons. So with 2 hidden layers, this is going to need 609 neurons. But then once again, once I capture these 64 boundaries, beyond that, it's just an XOR. So it's an XOR of 64 variables. An XOR of 64 variables can be done using just with just 190 neurons. So instead of needing 609 neurons, I could do this whole thing once I realize that it's an XOR with just 190 neurons. So Jack over here. This one, I have 16 lines. So I have 16 neurons in the first layer. And then I have 40 of these yellow regions. So I have 40 neurons in the second layer. So 40 plus 16, 56. Did that answer your question? I'm assuming so, right? So here, for example, I have 64 lines. So 64 neurons, 1 for each of these lines. And then I have 544 of these yellow cells composed by these lines. So 544 neurons in the second layer, so that's 609. But once I use it as a model, it as an XOR, it becomes much tinier. So the summary is that the number of neurons required in a shallow network is potentially exponential in the dimensionality of the input, worst case, or exponential in the number of statistically independent features. But if you go deep, the number of neurons can become much, much smaller. So adding to our lessons, multi-layer perceptrons are universal classification functions. Even a network with a single hidden layer is a universal classifier. But a single layer network may require an exponentially large number of perceptrons, more than a deep one. And deeper networks may require far fewer neurons than shallower networks to express the same function. They could be exponentially smaller. So in other words, deeper networks are more expressive. More layers are better, right? Now, let's go to the last one. MLPs as universal approximators. This is Boolean functions. These are classifiers. What about real-valued outputs? We already saw, for the case of a scalar input, that we can model scalar functions with a neural network. So a 3-unit MLP of this kind, so assume we have a scalar input, this 3-unit MLP can be configured to output a 1 between 2 thresholds and 0 elsewhere, right? This first guy fires if the input exceeds T1. The second fires if it exceeds T2. If you sum their outputs with weights 1 and -1, then if X is less than T1, the output stays 1 and stays 0 because neither of them fire. If X is greater than T2, both of them fire and cancel each other out, so the output becomes 0. In between, only this guy fires and the output is 1. And once you can compose this little step function, then you can get a stepwise approximation of any continuous function of a scalar input. Turns out that this doesn't generalize so trivially to multidimensional functions. So if I have multidimensional functions, I have to do this somewhat differently. We know that an MLP can compose, if I have infinite or a very large number of neurons over here, perceptrons, and I sum their outputs, then the output begins to look like this. This can compose a cylinder where where the sum is n over 2 inside the circle and 0 outside. And so if I have some multivariate function, then the way I would approximate the function is by filling the space with cylinders and scaling the cylinders up to different heights to approximate this continuous valued function to arbitrary precision. So this makes sense? Yes, no? Anyone? Okay. So Delphine, where did I lose you? On this. Okay. So did you understand this bit about how this networks out, this one, where the outputs of these neurons are just summed up, can compose a cylinder? So I can have one such network. I can have an infinity of such networks. Each one composes a different cylinder at a different location. Then this output can be scaled by the height of the function that we are going to try to approximate in the region of the cylinder. And all of these scaled outputs can then be summed up. And then when you do so, you're basically approximating this overall function by a sum of scaled cylinders. It's going to be scaling the weights of these outputs. That's right. Right? These outputs weights are these height of the function in the region. And so that's how you would do it. That makes sense? So there's just one hidden layer over here, right? Over here, the basic cylinder is n over 2. So you'd multiply it by some value that makes the height of the cylinder approximately equal to the height of the function over there in the region of the cylinder. And so, well, the point is, you can actually model a continuous valued function. It's not going to be exact. It's going to be an approximation. I can make the approximation error arbitrarily small, and I can model any continuous valued function with a neural network with just one hidden layer, right? So here's my fourth pole. Let's see if I can launch it. Can you guys see the pole? Okay, 10 seconds. All right. Let me end the poll and share the results. Here's what you guys thought. Can somebody give me the answer, true or false? True, false. Okay, those of you who said false, why is it false? It's an approximation. I can approximate the function to arbitrary precision, but it's never going to be exact. There's no guarantee that it will be exact. So the answer is false. It can only be an approximation, but I can make the approximation error as small as you want. So the cylinder height and radius is something that you can, so if I have a bunch of inputs, by adjusting the weights coming in to these neurons, you can actually adjust the location and the height of the cylinder. Okay, so the heights and the bias. This they're placed side by side. Okay. All right. So finally, here's a discussion of sudden depth and sufficient depth and width. So in the previous discussion, we showed that a single hidden layer MLP is a universal function approximator. It can approximate any function to arbitrary precision, but may require infinite neurons in the layer. More generally, deeper networks will require far fewer neurons for the same approximation error. This is true for Boolean functions, classifiers, and real-valued functions, but there are limitations, right? So how would we determine the weight of each cylinder? The weight of the cylinder is the output of the cylinder is going to be scaled to the height of the function in the region where the cylinder is. That's it. But the point is we are trying to make is that you can model a continuous valued function with a single hidden layer if you have infinite neurons in the layer. But the moment you go deep, you can get you need far fewer, right? So that's the point we're trying to get to over here, depth, okay? So for that, I'm going to go back to this decision boundary. Now, we saw that for this decision boundary, it's composed of 16 lines. So you need 16 neurons in the first layer to capture these 16 lines. There are 40 of these golden areas. So you need 40 cells in the second layer to compose each of these golden regions from the outputs of the first layer neurons. And so 56 neurons can compose this decision boundary exactly, right? But then suppose I decided that I'm not going to use 16 neurons in the first layer, I'm going to use only 8. Can I? And I'm allowing myself as many neurons I want in the subsequent layer and going as deep as I want in the subsequent layer. The only restriction being I'm using threshold activation perceptrons. Can a network of this kind, where the network is unrestricted after the first layer, but the first layer has only 8 threshold activation neurons, can this network capture this decision boundary? Can you do something here to make it capture the decision boundary? Why not, Rishabh? Why not?
Because you'll never get the decision boundaries for the lines that you want to draw in the first place. And you can add as many neurons, but that will only tell you where exactly those yellow regions are. So you'll never be able to recover from the loss of those lost lines.
So I think what he's trying to tell me is something like this, right? If I have only 8 threshold neurons in the first layer, each of these neurons is going to capture one line, correct? So it's only going to tell me whether I'm to the right of the line or to the left of the line, but it's not going to tell me how far I am from the line. And so these 8 neurons are only going to capture information of this kind. Once I go past this first layer, the only information that I will have remaining is in which of these regions I am, but I will not have any information about where I am in the region, because the threshold activation simply tells you you're to the right of this line or to the left of this line. Even if these 8 neurons were to capture these 8 boundaries, which form a crosshatch, by the time you cross these neurons, the only information that remains is which of these various cells you are in, but you have no information about where you are within the cell, right? They can't tell you where you are within the cell. And so the information that's required to form the finer crosshash is lost. There's nothing you can do downstream to recover that information. That makes sense to you guys? There's a 1 thumbs up, right? Okay. So similarly, right? Let's say I continue to use 16 neurons over here, but I decide to use fewer than 40 neurons over here. Can I get the crosshash? Once again, in the worst case, the answer is no, right? Because there are 40 regions over here. So basically, every layer must be sufficiently wide in order to capture the function. But then let's go back to this issue of why you need enough neurons and how to fix it, right? So let's say I decided to have only 4 neurons in the first layer. If we use a threshold activation, the threshold activation only tells you whether you're to the left of the threshold or right. but it doesn't tell you how far you are from the threshold. So that by the time you get to this dotted line, you'll only know which region you're in, but you're not going to know where you are within the region, which means that the rest of the network has no information to operate on to create the rest of the boundaries. So given this, how can you fix this? Anybody? We need the activation function to be graded. It's not enough for us to say, for it to say whether you're to the right of the threshold or not. You need information about how far you are from the threshold. And so continuous activation functions result in graded output at the boundaries. This provides information to subsequent layers about how far you are from the boundary. This is info, right? And so subsequent layers can operate on it. And again, over here, not every activation function is good. So look at this. This is a sigmoid. The sigmoid does give you information about how far you are from the boundary, but that information saturates very quickly, right? Or here's a ReLU. A ReLU is better. On one side, it continues to give information forever about how far you are from the boundary, but on the other side, it's zero. So uh, even the soft version of the ReLU, the soft plus, gives you information primarily on one side, but on the other side, it quickly saturates to zero. So what would be an even better activation? Something that gives you information on both sides about how far you are from the boundary. That is, for example, this leaky ReLU, which has two different slopes on either side of the boundary. But on either side, you're going to continue to have information about how far you are from the boundary as you keep going away from the boundary. And so once that information is provided, even if it's a narrow layer, there is information being provided downstream so that subsequent layers can recover more of the information about the decision boundaries. And so narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded, but that means that downstream the network has to have greater depth to permit later layers to capture patterns. Again, keep in mind that this is not a guarantee. So for example, if I want to capture this crosshash, this crosshash, and I'm using 4 neurons, and the 4 neurons are giving me graded information from the boundary, but the boundaries end up being parallel. There's no way I'm going to be able to recover changes orthogonal to these boundaries. So while they help, they're not a guarantee, right? And so does this make sense? All of this, what we've said so far. Yeah. So the first layer gets the number of edges, and the subsequent layers get the number of squares. Pretty much, yes, right? And so MLPs are universal function approximators. They can model any Boolean function, classification function, or regression. Deeper MLPs can achieve the same precision with far fewer neurons, but must still have sufficient capacity. The activations must pass information through. Each layer must be sufficiently wide to convey all relevant information to subsequent layers. So, did all of this make sense? Where if you restrict the first layer in the XOR, you still needed 2 neurons, right? With 1 neuron, there's nothing you can do because you got only one boundary. Now, and so here's your final poll. Let me see. Collateral statements. Okay, 15 seconds, guys. I will go over by maybe a minute. Please bear with me. 5 seconds. All right, I'll stop this. Here's what you guys thought. Okay. As this first statement, a network with an upper bound on layer width can model any function by making it sufficiently deep. True or false? This first one. False. Second one, networks with graded activation functions are more able to compensate for insufficient width. True. We can always compensate for limits in the width and depth by using more graded activations. True or false? False, right? And for a given accuracy, networks with more graded functions will generally be smaller than those with less graded activations. True or false? True, right? So only the second and fourth statements are true. So we have this notion of a capacity of a network. What can a network model is defined in terms of information capacity, VC dimension, what have you. There's been a ton of work on it. But in general, a network with insufficient capacity cannot exactly model a function that requires a greater minimal number of convex hulls than the capacity of the network. Lots of work on capacity. We won't go through it. But here are the lessons for today. MLPs are universal Boolean functions. The universal classifiers, the universal approximators. What I mean, function approximators. What I mean by this is that if you give me any Boolean function, I can always compose an MLP for it. Give me any classifier. I can always compose an MLP that captures the classification boundaries with arbitrary precision. Give me any real valued function. I can compose an MLP that can approximate it to arbitrarily small error. And a single layer MLP can approximate anything to arbitrary precision, but could be exponentially or even infinitely wide. Deeper MLPs can achieve the same precision with far fewer neurons. That is, they're more expressive. More graded activation functions result in more expressive networks. And so we're going to stop here. We know that MLPs can emulate any function, but how do you make them emulate a specific desired function? This is the business of training an MLP. That's what we will begin with in the next class. I'll stop here and take any questions, but before you leave, just do me a favor. There are still 250 of you in the class. Give me a thumbs up if the lecture made sense mostly. I'd like to see 100 or so of you to just agree with me, or I've lost you guys, right? So I'm still at 75. Mostly. I did say mostly, right? But if you go back over the slides and the lecture, it should all kind of make sense. So everything flash by. I will wait for a couple of minutes after this. Let me stop recording and answer any questions.